Hello all. This is John Noguera. I am the Chief Technology Officer and co-founder at SigmaXL. Today's webinar, we are introducing the new features in SigmaXL version 7. The first area is in the automatic assumptions testing for t-tests and ANOVA. So we have red light, yellow light, green light, or red highlight, yellow highlight, green highlight, for the various aspects on the assumptions of a t-test and an analysis of variance. Green means everything's okay. Yellow is a warning, just something to look at. And red means it's a serious violation and you really need to take action. We consider normality, robustness to normality based on sample size, outliers, randomness, and equal variance. So each of these, of course, we'll look at in more detail. We'll start with a high-level overview, and then we'll look at each of these new features in greater detail. The attribute measurement systems analysis, we did have binary MSA, and we've added ordinal and nominal. But what's nice now is that we have highlight for kappa and for Kendall's coefficient. So in the binary and nominal, the focus is on kappa. And for ordinal, we have highlights on Kendall's correlation. So again, green light means good agreement, yellow light means barely acceptable, and a red highlight means that there's a problem and corrective action is needed. We also, in version 7, added what's called an effectiveness report, where each appraisal is considered uniquely. That is, we do not require agreement across all trials and agreement across all appraisers, but treating each appraisal as an opportunity, how well does the measurement system do? So we call that an effectiveness report. We also added to Pearson and Spearman correlations a highlight. And the basis for recommending one or the other or neither is if the data are normal, but bivariate normal, and that's important, that not just normal for the individual variables, but when you're dealing with a correlation, Pearson assumes bivariate normality, and so we test behind the scenes for bivariate normality, and if the results are significant and the data are bivariate normal, then Pearson is highlighted. So here in this example, you see some yellow highlights. We're saying that Pearson is the appropriate correlation to use for these correlations. And then down here, these highlights, they failed on the bivariate normality test, and so Spearman is being recommended for those correlations. So it answers the question that is often asked, when do I use Pearson, when do I use Spearman? And of course, you still need to look at your data graphically, but this simplifies the process by having an automatic bivariate normality test built in and then just simply highlighting the appropriate test to use. Also, something that we're quite excited about are called exact statistics. Many of you are probably aware that when you run a chi-square test, one of the assumptions is that at least 80% of the cells have to have expected counts greater than 5. So in other words, if more than 20% of the cells have expected counts of less than 5, chi-square is unreliable. And often you'll hear people say, well, just collect more data or consolidate categories. And that really is a Band-Aid. And what we have done is we have put together in our package what are called exact statistics based on permutations. So we're no longer relying on the large sample chi-square, but using permutations, we compute the actual exact p-value, Fisher exact, or on the Nonparametrics, the appropriate statistics, say for Mann-Whitney or Kruskal-Wallis. So basically, it means that you have a p-value that you can trust when you're dealing with small samples. Okay, so that's the overview of the new features. So now what I want to do is I want to just kind of go through step by step on each of these. All right, so the Automatic assumptions check for t-tests and ANOVA. Normality. What we do there is very simple. If the Anderson-Darling p-value is less than 0.05, then you're rejecting the null hypothesis of normality. And we highlight that as yellow. The reason I do that is because you can still be robust to non-normality, but we want you to be aware that you have some non-normal data. So automatically, if you see yellow in the normality report, that's an indication of non-normal data. And we also then report the skewness and the kurtosis. If the p-value is greater than 0.05, greater than or equal to 0.05, then the cell is highlighted as green. So green is good. All right, so in version 6.2, we added some templates for tests for robustness. And what we did was we did extensive Monte Carlo simulations with varying degrees of skewness and kurtosis and a range of sample sizes from 2 to 2,000. Each t-test or each ANOVA had 100,000 replications, and we incremented the sample size to the point where the alpha, the observed alpha, was within 20% of the target alpha. So if, for example, a false alarm rate of 5%, we said that if alpha was between 4 and 6%, we would consider that robust. So that's how we define robustness. So all that work that was in the templates, robust t-test and ANOVA, minimum sample size, we built that in, so now it's done automatically. And you get the report if sample size requirement, if the sample is greater than the minimum, it's green. If it is less than the minimum, then it's red. So saying, look, you have non-normal data, and you do not meet the minimum sample size for robustness. So that's given to you as a warning. And then also we recommend the appropriate non-parametric test. So in the one sample case, it'll either be Wilcoxon or the sign test, and that depends on other things like symmetry. And then in the two sample case, we'll recommend the Mann-Whitney, and in the multiple sample, we'll recommend either the Kruskal-Wallis or the Moods median, depending on whether there are outliers. And that's all done automatically. So on the outliers, we use the box plot rules. If there are no box plot outliers, then it's green. One potential outlier is 1.5 times the interquartile range. And then a likely outlier is 2 times the interquartile range. That one is not seen on the box plot. However, we do report it as a likely outlier. And then we have the 3 IQR, and we call that an extreme outlier. Okay, so you have potential, likely, and extreme. And if it is potential or likely, it's highlighted in yellow. If it's extreme, it's highlighted in red. Another little thing that we do that's kind of nice is we then remove the outliers automatically and retest for normality. And if the data are normal minus the outliers, we tell you that. Now, we still highlight it in red or yellow, but point out that your data actually are inherently normal if the outliers are excluded. Now, I'm not saying that you can just remove the outliers, but it's good to know that your non-normality may be due to outliers. So that's something that is given in the report. Another test that is included is test for randomness, serial independence, and that's the non-parametric runs test. So if the p-value is greater than 0.05, we're good. We conclude that the data are random. If the p-value is less than 0.05, we highlight that in yellow. If the non-parametric runs test p-value is less than 0.01, we highlight that in red. So we're saying that the 95% confidence, we're calling that yellow, and at the 99% confidence, we're calling that red. There you would look for a trend. You would look for something that obviously you'd want to look at your data with run charts, with other graphical tools. This is all a text report, and the point is that we're not trying to replace the graphical analysis, but give you a nice highlight summary of the status of your of the assumptions of your t-test and your ANOVA. Finally, in the two-sample or multiple sample case, we do a test for equivariance. And if you're running an equivariance test and the data do not have equivariances, then a warning is given. If you have unequal variance in the data and you're not using the right test, then we'll give you the appropriate warning for that. All right, so let's look at an example now. I'm going to go in and run the customer data is what we have in our workbook, and I'm going to do an analysis of variance of overall satisfaction by customer type. SigmaXL, statistical tools. So the menus for these particular items have not changed. There's no difference here. The difference is in the dialog where you have a display test assumptions report. Overall satisfaction by customer type, and then I check test assumptions report. And this is my report. Everything is the same now. We just have this new text report. And most of it's green, so that's good. We just have a couple of cautions here. For example, for customer type 2, that you have some non-normal data and there's a potential outlier. So it is robust. There's a potential outlier. And this is the sort of thing that you would then go back and you would do your standard graphical analysis. So I could do, for example, a box plot and overall SAT by customer type. Oh, and there's my potential outlier. Please note, as I mentioned, we, in addition to identifying potential outliers in the report, will also give you what we call likely outliers. But the box plot only separates the 1.5 IQR and the 3 IQR, so the potential and the likely will both show up as the light circle, and the extreme will show up as the solid circle, or the solid dot. So that's test assumptions for one-way ANOVA. Let me pull up a one-sample test with some non-normal data. So I have small sample non-normal data. So this is a task time, and it's a difference in task time before training versus after training. So we're going to do just a one-sample t-test on this difference in task time. So you could have done a paired t-test if you had the before and the after data. So this is the difference data. So again, I'll just go to statistical tools, one-sample t-test. And in this case, I'm going to do the difference. I'm going in with a specified null hypothesis of 0. I'm going to change this to, the alternative is to less than, because it's a one-sided test. And I will again display the test assumptions report. So this is the one-sample t. So again, we have all our regular statistics. Now in this case, we have non-normal data, and it fails the robustness test. So what's happening here is actually, it's not a skewness problem, it's a kurtosis problem. It's failing the robustness test. It would have needed a larger sample size, 16 versus the 15 in the actual data. There are no outliers, and the randomness test is okay. So what's being recommended is the one-sample Wilcoxon. And in a little bit, we'll run that one-sample Wilcoxon test. So because of the fact that you have non-normality and it's not robust, the Wilcoxon test is being recommended. So just a quick one, if I do a histogram of this, you'll see what's happening with this particular data. As you can see, it's kind of a uniform distribution or possibly bimodal. It's a small sample size, so you wouldn't want to call it necessarily bimodal, but it's looking more like a uniform distribution rather than a normal distribution. And that's why it was triggering as not normal because of the kurtosis rather than your more typical skewness problem. And because of the fact that it's symmetrical, the Wilcoxon is being recommended rather than the sign test. The nonparametric Wilcoxon is being recommended. If it was a skewed distribution, we would have recommended the one sample sign test in the report. So those are the red, yellow, green for the t-test and the ANOVA. Now I want to switch gears and talk about the attribute measurement systems. All right, so in the attribute measurement systems, as I mentioned earlier, we have a red light, yellow light, green light, and we've added the nominal and the ordinal attribute measurement systems. The nice thing about this, when you're looking at an attribute MSA report, there's a lot of information. You have your percent agreement, your confidence intervals, you have kappa scores, and especially for somebody just starting, it can be very overwhelming. And so we provide all the information, but by putting in the yellow, green, red highlight, right away you can see how well your attribute measurement system is doing. So the coloring allows you to immediately see if a particular appraiser is a problem, or if it's a problem, against the standard agreement and so forth. So whether it's a repeatability problem, a reproducibility problem, you can see that. We've added types of confidence intervals. Basically, in the templates of version 6.2, when you're doing a two-proportion test, we allow you to run an exact confidence interval or a Wilson score confidence interval. Now, the nice thing about the Wilson score is that it is a more powerful in that the confidence intervals are narrower. When you're dealing with attribute MSA, that's actually a plus because often your sample sizes are small, and you really want the most powerful tools at your disposal. What Wilson score does is it gives you an average. It's using average of 95% coverage rather than a minimum of 95% coverage. So exact is very conservative, whereas Wilson score it gives you an average of 95% confidence. And for that reason, a lot of practitioners prefer the Wilson score. So that's just something we've included as an option. If you want to match Minitab, use the exact. If you want to match jump, use the Wilson score. And I mentioned the attribute effectiveness report, where you do not have to have consistency across trials or across appraisers, and that allows for narrower confidence intervals as well. So that's treating each appraisal as a unique opportunity. The nice thing there is that you get actual type 1 or type 2 misclassification. There's no such thing as a mixed error anymore because it's either a good part being called bad or a bad part being called good. And we talked about kappa. We've added the highlights, and I'm just going to skip over these slides, just a little bit of background, how we chose our numbers. Basically, less than 0.7 is considered poor. Between 0.7 and 0.9 is acceptable, yellow. Above 0.9 is very good, green. And then for ordinal, we have the Kendall correlations. And there's two kinds. There's what's called Kendall's concordance. And Kendall's concordance is used when you have an unknown, or there is no reference standard. For example, comparing two appraisers. And Kendall's correlation is used when there is you're comparing against a known standard or a known reference. There are slight differences here. I don't want to get into all the details, but for concordance, we use less than 0.7 is red, greater than 0.9 is green, so that's actually the same as the kappa. And for correlation, it's a little bit different. Less than 0.6 is unacceptable, and greater than 0.8 is acceptable. These were determined using Monte Carlo simulation to come up with the rules of thumb for Kendall's correlation. So slightly different values. Again, the important thing is if it's red, it's poor. If it's yellow, opportunity for improvement, and if it's green, it's good. One other thing we've added is we've added confidence intervals to the kappa scores as well as to the Kendall scores. So with that, let's have a look at an example. We'll start with the binary example that's in the workbook, and that is the Automotive Industry Action Group dataset, Attribute MSA AIAG. All right, so we have three appraisers, And we're using 0 and 1. 1 is a good part. 1 denotes a good. 0 is bad. So we're going to do measurement systems analysis, attribute MSA binary, and part, appraiser, assessed result, true standard. And one thing that we've added is the ability to specify what the good level is. And that's important because then your type 1 and type 2 information, we can tell you whether you're calling a bad part good or a good part bad. So here's the confidence interval types that I mentioned, Wilson score or exact. I'm going to stay with Wilson score. So we have added graphs with the confidence intervals. So this is the percent confidence interval within appraiser agreement. This is the each appraiser versus standard. This is the effectiveness number. And remember, effectiveness is different in that it's treating each appraisal as a unique opportunity. And then we also have confidence intervals on the kappa scores. Note the scales are different. Obviously, sense at 0 to 100. And for kappa, we only show 0 to 1. Even though kappa can be negative, we only display positive numbers because typically on an attribute MSA, you expect to have some positive agreement. You generally don't have complete disagreement. So it just makes for a nicer graphical output. So here we have our highlights. Lots of yellow. There's appraiser B does quite well against the standard. So this is a measurement system that there's opportunity for improvement. It's not a bad measurement system. There are no reds, but it's certainly a measurement system that could be improved. Again, just makes it very easy. This is a classical report, the top half, but far better to use percent effectiveness. And if it's more than 95% effectiveness, that's very good. If it's less than 85%, that's unacceptable. That's actually correlated to the kappa. So we highlight the kappa scores and make it easier in terms of overall assessment of your attribute measurement system. Now, something we've also added that is very, very useful. One is a summary table telling you that if the standard is bad, that if it's truly bad, how often did you call it bad? If it's truly good, how often did you call it good? If it was truly good, but you called it bad, how often did that occur? And if it was truly bad, how often did you call it good? So that's a summary, a misclassification summary. And what I really like here is this table for each part. If there's any discrepancy, if it's yellow, you're calling the good part bad. If it's red, you're calling the bad part good. Calling a bad part good is actually a worse error. Type 2 error is worse than type 1 in general. So if it's green, it's agreement. Right away, you can see if one appraiser is doing better than another, or our particular parts being more problematic than others. So it's just a nice, simple color coding that you can look at to supplement your traditional attribute gauge on our reporting. So that's the binary attribute MSA. Now, what I want to do is give an example with ordinal attribute MSA. So we'll go measurement systems analysis, ordinal, and so again, sample, appraiser. Here we're using a 1 to 5 scale, so it's grading parts from 1 denotes very poor quality, 2 is poor, 3 is fair, 4 is good, and 5 is very good quality. So it's an ordinal scale. We have an expert reference, so we will include that in the analysis. Again, you have your graphical outcomes. Where you have 4% agreement. Ordinal, it's very easy to get a low percent agreement score or percent effectiveness score. So what we focus in on with the yellow, green, red is the Kendall's coefficient of concordance or the Kendall's correlation coefficient. So clearly, Mo is problematic, Joe is nominal, and Sue is doing quite well. So you can, again, just see that right away. Yes, there's a lot of information here, but the color coding just helps you to hone in on where are we doing well, where are we not doing well. We also have a color code for the raw data. And here you can see Sue doing quite well. Mo has a lot of red, and Joe is kind of in between. The definition of green means that you match the expert reference. Yellow is that you were within one of the expert reference. And red is if there was a deviation of 2 or more, it's highlighted as red. So again, that's the color coding for the raw data for ordinal attribute MSA. I'm not going to give an example of nominal. That's basically just similar to binary, but extended because you have multiple levels. So if you have 3 or more unique categorical levels, then each of those are considered. The next item in version 7, that's the Pearson versus Spearman. If you're doing a correlation study and the data are bivariate normal, then we recommend Pearson. If the data are not, and that can either be due to non-normality or it can be due to outliers, then we're recommending the nonparametric Spearman. Now, please note that the only correlations that will be highlighted will be significant correlations. If the correlation is not significant, then there will not be a yellow highlight. You obviously want to look at your data graphically with scatter plots when you're doing a correlation study, whether it's for outliers or unusual patterns. You want to be able to see that, and that's one thing. It's nice to get a summary report in the correlation matrix, but you always want to complement that with a scatter plot matrix. So the last thing that we're going to discuss are the exact statistics. So if you have a small sample and you're doing chi-square or you're doing nonparametric tests, then normal traditional statistics can be misleading, and exact statistics are appropriate. Where we've added exact statistics are on the nonparametric, the one sample sign test, the Wilcoxon sign rank, the 2-sample Mann-Whitney, Run's test, Kruskal-Wallis, and Mood's median all now have exact statistics as available as options. And underneath the hood, we're using what are called network algorithms to speed up the computations. So that's something that we don't necessarily have to solve all permutations. There are tricks that you can use, algorithmic tricks, to speed up the process so that you can still get an exact p-value but not necessarily have to solve all permutations. One important note, when you're using exact statistics, this does not mean that you've added power. It's eliminated a source of error due to small sample size, but it doesn't mean that you have a more powerful test. Power only comes through sample size. And now, if you fail to reject the null hypothesis, it could be because you had insufficient power to detect. So keep that in mind. On the other hand, you have expensive data collection and you have a small sample and this is all you have. You really want to make the best of the analysis with the data that you have. Then exact statistics are the way to go. There is kind of an intermediate category where exact statistics are computationally too intensive. It would take you hours and hours to solve the p-value, but the sample size is still too small for regular large sample statistics to be valid. And in these cases, we provide an option called Monte Carlo p-value. So by running 10,000 or 100,000 simulations, we give you a Monte Carlo exact p-value with a 99% confidence interval. Now, please do not confuse the confidence interval here with a regular confidence interval. A regular confidence interval is on the statistic. This is the confidence interval on the exact p-value. And you'll see that in some examples coming up. So here are some guidelines in terms of when to use exact. For example, in a Wilcoxon signed rank test, if you have 15 or fewer, you should use an exact. Mann-Whitney, if each sample has 10 or less, you should use exact. Kruskal-Wallis, 5 or less. Mood's median, 10 or less. And Run's test, less than 50. In the chi-square, A rule of thumb is when more than 20% of the cells have an expected count of less than 5. So in version 6.2, we included Fisher's exact for the two proportions. Now we've expanded it so Fisher's exact will work on a full contingency table or two-way row by column or pivot table. Of course, more information on this in the appendices of the workbook. And with that, we'll look at some examples. We'll go to the data set, that non-normal task time data set that we started with. Back to the data. And the report highlighted or recommended a one-sample Wilcoxon exact. What we're going to do, actually, we're going to start with a regular Wilcoxon. And then we'll do the Wilcoxon exact. So I'll go to non-parametric tests, one-sample Wilcoxon. And again, it's the null hypothesis is 0, it's a difference, and the alternative is less than. So according to this Wilcoxon analysis, there is no difference, or no significant difference between the before and the after. Now, we will rerun using Wilcoxon exact. So again, we'll go down to non-parametric test. This time, non-parametric test exact. One sample Wilcoxon exact. And we'll run that. And, you know, it's not a lot of difference, but notice now it is less than 0.05. And so the key thing here is that the exact gave you a different answer, but the exact is the correct answer. And by going to the exact, you can see that it's indeed a reject of the null hypothesis. So that's the one sample Wilcoxon. We also have another example, which is I'm going to use a data set that was from a dental study called oral lesions. And I'm going to do a chi-square analysis on that data set. So I've relabeled the oral lesions to just A, B, C, D, E, because basically this could be like product defects instead of medical problems. And region 1, region 2, region 3, I did just generic. The data was actually derived from some studies in India and published in a dental journal. As you can see with this data set, this is count data, but you have zeros and you have lots of small numbers. And that's a big problem for chi-square because remember, chi-square expected counts have to be, the majority of the expected counts need to be greater than 5. So let's go ahead and run this. I'm going to run the exact, and the nice thing about the exact is that it does give me both the regular chi-square value as well as Fisher's exact. So I'll go to Statistical Tools, chi-square test exact, and this is already a two-way table. If you have raw data, you would use chi-square test Fisher's exact, but because I already have a pivot table or a summary table, I'm going to go with chi-square test two-way table data. And I'm going to use exact here. By the way, when you run exact, you have the ability to increase the computation time. Typically 60 seconds, most problems will be solved, but if you have large data, you're going to need more time. However, I would caution you that if you start getting into large problems, some of those things could take hours, and that's where you need to use Monte Carlo exact. So let's just run this. First of all, notice the expected counts. A lot of them are less than 1, and that's bad because none of them should be less than 1. And there's only 2 of them that have expected counts greater than 5. Clearly, this is a problematic data set. And where you see it, here's your chi-square p-value. Your regular chi-square p-value is 0.14. That's a clear fail to reject. But the Fisher exact p-value is 0.01. Strong reject of the null hypothesis. So it's a nice example to show just how much of a difference you can get when you're assuming a large sample and using chi-square when in fact with small samples you need to use the exact statistics. So what I'm going to demonstrate next is use of Monte Carlo simulation. Now this was solved very quickly, so it's technically not necessary, but I like to just to illustrate how the Monte Carlo works. If we switch over to Monte Carlo exact, You have your confidence level for the p-value, and the default is 99%. Keep in mind, what this is the true exact p-value will lie somewhere within this confidence interval. It is not the same as your confidence interval on your test statistic. It's going to report the Monte Carlo p-value and the confidence interval on that p-value. So I have 0.0082 to 0.013 is my 99% confidence interval, and my estimate is 0.0106. All right? So Monte Carlo is an approximation, but giving you a 99% confidence interval, you know that somewhere in that interval, most likely, exact true value will lie. So that's the Monte Carlo exact. And that concludes my presentation. In summary, we have the red light, yellow light, green light on the t-tests and the ANOVA with the various assumptions. We have the highlight of the Pearson versus Spearman correlation. We have the addition of ordinal and nominal attribute MSA, and we've added the red light, green light, yellow light, or highlight to make the interpretation much easier. Also, we've added the effectiveness report in attribute MSA, particularly beneficial for binary attribute MSA. And we've added the exact statistics for small sample. So when you have a small sample problem, you know that the p-value is correct, that it's not just a rough approximation. So then we'll call the webinar, we'll call it a wrap, and I thank you all very much for your attention and for your attendance. The PowerPoint is available immediately, and the data sets, the examples that I've used are all in the workbook, and the data sets are available with the installation of version 7. So with that, again, thank you all very much for your participation.